All right, in this video, we're going to talk about gas stoichiometry. Well, I don't know what the heck that's supposed to say. Anyway, gas stoichiometry. Remember, several weeks ago I said if you are unable to do a stoichiometry problem, you are in danger of failing the class because this is one of those things that comes up over and over and over again. And here it is again. I'm not lying to you guys. I'm trying to help you out. I promise. Okay. So let's just work our way through this problem. I'm going to give you an example. We'll work our way through it. So what volume of CO2 is produced when 1.0 grams of sodium carbonate is combined with 100.0 mLs of 0.15 molar HCl at STP. Yeah, we probably couldn't actually do this problem at STP because it involves solutions. 0 degrees Celsius, things might be a little, well, they wouldn't be frozen because it's a solution, but it might be a little chilly. So let's look at the chemical equation. 2HCl aqueous. And the phases kind of matter here because we're doing gas laws. We got to find the gas. I'm sure you guys all recognize that it's CO2. But anyway, NaCl, and we get some water. There we go. So let's just go through and look at the problem real quick. Okay, we're asked for a volume of CO2. A volume of CO2. That's different than other stoichiometry problems because usually we're asking for like a molarity if it's a titration problem, or we might ask you for a mass. At the very beginning of the semester, that's what it would have asked for. But it's a volume, so because this is gas stoichiometry, and we're given a temperature and a pressure, and in our reaction we produce a gas. So this starts off the same way as any other stoichiometry problem. All right, and this isn't just a stoichiometry problem, by the way. This is a limiting reactant problem. How do we know it's a limiting reactant problem? Well, we're given two different reactants, amounts of two different reactants. So if you remember way back, we got to convert both of those, the Na2CO3 and the HCl, we got to convert them on paper into CO2. So let's go ahead and do that. This first step, you should, actually, both of these first two steps, you guys should be able to do no problem. If you wanted to pause the video and see if you can get moles of CO2, that would be a great first step, okay? So 1 gram Na2CO3, we're going to multiply by 1 over the molar mass, or 1 mole of Na2CO3 over 106.0 grams of Na2CO3. And what do we come out with? Oh, I'm sorry, that's not the end of the problem. So that gives us moles of Na2CO3, but we got to get to CO2. Okay, remember there's a 1 there and a 1 there. So this is a 1-to-1 ratio. Can we just skip this step? No. When you've been a chemist for a few years, yeah, you can skip this step because you can do it in your head. But at this point, no, we show all of our work, even though it can be a little tedious. Just think, I do this every semester for years. You guys only have to do it once. Anyway, there we go. We got 0.00943 moles of CO2. Hopefully you are able to get that on your own. Now let's jump over to the HCl. Okay, do the exact same process, but for the sodium carbonate, the Na2CO3, we're given a mass. For HCl, we're given a volume, and this is the volume of a liquid, a solution, and we're given the concentration. So we're going to use both of those things to convert to moles of HCl. So we have 0.1000 liters of HCl. That's just 100 milliliters converted to liters. And remember that molarity, where should I write this? I'm just going to go over here. Molarity is equal to moles over liters. So we can write molarity as a conversion of 0.15 moles HCl per 1.0 or what, just one, I guess is fine, liter of HCl. Then again, we need our stoichiometry or our mole ratio. That's the whole point of a stoichiometry problem, is using that mole ratio. So 1 mole of CO2 per 2 moles of HCl. That, again, straight out of the balanced chemical equation, okay? We got the 1 mole of CO2 and then the 2 moles of HCl. And I come out with 0.00750 moles of CO2. Now, up to this point, this is 100% review. I have not done anything new, okay? You guys should all be with me on that. I know some of you are probably rolling your eyes at me. That's okay. Now, what do we do with these two numbers? Add them together? Definitely never, ever not do. Don't do that. I don't know what that meant, but don't do that. Okay, we want the smaller amount. Remember, this is like the sandwiches. We can make the fewest number of sandwiches here. So cross out the most amount, circle that least amount. We're going to take that least amount and we're going to use that in our next step. Our next step is to use the ideal gas law. PV equals nRT. Okay, because if we go back up to the original problem, what volume? We're looking for a volume of CO2. So we're going to solve for V. V is equal to nRT over P. Now all we got to do is plug and chug. What number do we plug in for N? That moles of CO2 that came from the limiting reactant. So we have 0.00750 moles, and I'm just going to leave it as moles, not moles of CO2. R 0.08206 liters times atmospheres divided by Kelvin times moles. Temperature at STP, hopefully you remember, is 273 Kelvin. Remember STP, 1 ATM, 273 Kelvin. That's 0 degrees Celsius. And then our pressure, 1 ATM. I just like to go through and cancel out the units just to show that it really does matter what you use for R. Okay, and the way you know you're using the right unit for R, or the right value for R, is that you get the right unit at the end. So I come out with 0.168 liters. And that's my answer. Okay, let me show you one quick alternative way to solve this problem. Again, taking that moles of CO2, the 0.00750 moles CO2. Because this is at STP, we know the molar volume of any gas, any ideal gas, and we assume all gases are ideal until we get to the very end of the chapter, and I'll tell you otherwise. But for homework and exams, all gases are ideal. Okay. We know the molar volume of a gas is 22.4 liters, and if you don't know where this is coming from, go back and watch that molar volume of a gas video per 1 mole. Hello. Moles cancel out. And guess what we get? 0.168 liters. That only works at STP though, okay? Just keep that in mind.